Hello, we are group 6 and we're gonna be talking about cardinality. My name is Carlos Leon and my group name is Monica Navarro and Elizabeth Purser. Um, to start off with, we chose this topic because one, it ties up with the set of theories that we have learned. Uh, it also uh it also defines the sets that contains in an infinite element, and it figures out two or more sets that have equal cardinality. Um, and first of all, we have to know what is cardinality. And and cardinality, I'm sorry, it's really hard to write with the mouse. Oh God. Okay, so cardinality, the way that George Cantor generalized it as, he says that it is an infinite set of of A that depends on the number of elements that are within the set, which the set of usually depends on denotes by the using of absolute value. For instance, to find out the cardinality, we have to write it as absolute value of A, which the two absolute value, it just means cardinality. And so now if we do it in an example, um, let's say the set of A is equal to the element 1, 2, 3 is the set of is so the set of A is 1, 2, 3, then the card oh my God, the cardinality of A is going to be 3 because there are 3 elements that are within a set.
So we're going to talk about same cardinality, and the definition is when we have two sets, and let's say those sets are A, and that set A is going to be equal to set B. And in order for these two sets to be equal, is if those two sets, if there exists a bijective function between the two sets. And when we have a bijection, that means that the function A onto B is surjective as well as injective. And I'm going to briefly summarize. So surjective is basically when we have two functions, or two sets, sorry, A and B, and it's going to be onto. So for every A in A, there exists at least one mapping to a value in B. But it can mean that at least one, so it can be, there could be another A that maps onto two B's. and that's onto. And then it's injective. We have two sets. And for any A value in A, there is at most one B value in B. But there can also be a B value where there's nothing mapped onto it, and that's still a one-to-one. Okay, so we're going to go right into the proof. So let's say, let me zoom in a little bit. So let's prove the same cardinality of A onto B. And let's say the function is 2x plus 3. So basically, what we're going to do is we're going to prove that that this function is both bijective and injective. So for injective, we're going to take x and y, and they're going to be in the real number set. And we're going to assume that for every f of x, there's going to be an f of y. So what we do is we just plug in the value 2x plus 3 is equal to 2y plus 3. And we simplify and we cancel out these, and it ends up being x is equal to y, which proves that for any y, we're going to get at most one x it's going to map on. Okay, so we proved that it's injective. So now we have to prove that it's bijective. And to do that, we have to take some y in R in the real number set, and we want to show that y is equal to f of x. And so we can do that. We know y is equal to 2x plus 3. And then if we solve for x, we get y minus 3 over 2. And we plug that back into the equation, where y is equal to 2 times x. And we get y is equal to y. And then that's our proof. And so by proving that it's both surjective and injective, we know that the set is bijective. and therefore they have the same cardinality.
So we're gonna be talking about infinite sets, and infinite sets is basically when set A is countably infinite only if set A has the same cardinality as n, which is the natural number. So if we end up proving this, so if we will prove this, we will have something like let cardinality A equals the set of n plus the subset of n, um, n, which is a natural number, when we will have the numbers 1, um, 2, 3, and so on until we will get something like n at the end, which is just saying infinite numbers because it just keeps going. Uh, but then we will also have another cardinality, and this will be cardinality B. And for cardinality B, it's going to be all positive, all positive odd numbers. Okay. So then if we have this, the proposition of this, so the proposition of this is saying that all positive odd numbers is equal to the number of so all odd numbers is equal to the number of natural numbers. Okay? And therefore we must prove, so we must prove that cardinality A and cardinality B are 1 to 1, or 1 to 1, and the cardinality A is into cardinality B. Okay? So first of all, we must assume that cardinality A, my bad. We must assume that A is into B if A is not equal to B and and f of A is not equal to f of B. Okay? So if we end up proving this, we could do it an example like saying let A equals 1 and let let um uh and let b equals to 3 and let 3 equal to 3. um so if we will prove this, we can say that when f of a is equal to 2 plus 1, which is this one right here, so this one right here, plus 1 is going to be 3, and oh, I'm sorry, I meant to write 2, not 3. I don't know why I write 3. And b, and then f of b would be something saying 2 plus 2, I mean times 2 plus 1, which that would be 3, I mean 5. Wow, 5. And then this answers right here, you can already see that f of a and f of b are not equal to each other. And even before that, when we let a equals 1 and b equals 2, you can see that a and b are also not equal to 1. So therefore, this function is a 1-to-1 function. Okay? And now if we will have to prove, so now if we prove that cardinality A is into cardinality B, then it's a surjective, then these two are surjective, and therefore the domain and range of the function of both functions, I mean of both sets, my bad, are equal to each other, and therefore the element, I mean therefore A is is a member of cardinality A, and B is a member of cardinality B. And this proves right here, so this right here proves that A, cardinality A, and cardinality B are both countable. There you go.
So what is infinite countability and infinite uncountability? Well, as we define up here, infinite countability is when two sets have the same cardinality, no matter how many elements there are within those two sets. As long as there's same cardinality, they're countable. Infinite countability is when there is no one-to-one correspondence between the sets of natural numbers. And as you'll see later when we use Cantor's diagonal theorem or his argument, we will find a list of infinite numbers that are not between the interval of 0 and 1. Usually the countability of infinite sets have much smaller cardinalities compared to those of uncountable infinite sets. So now we'll move on to proof of countability. So let's consider the following sets, C and D, and as well the function defined as f of x equals 36x. Well, in our lecture document here, we proved that these two sets map onto each other with the definition of the function by first proving that it is injective, or one-to-one, and surjective, onto. So since there's a bijection and it has the same cardinality, then both of these sets are countable, no matter how many elements there are in each set. So now I will provide an example. So let's assume that we have a function f of x equal 3x minus 1, and that we have a set of t equal the elements 2, 5, 8, 11, and so on. Now, our question here is if the set T is countable. Well, let's give examples to see if there's a mapping. So let's say we have another set defined in F that we call P, and see if P maps to T. In this case, where P is going to equal 1, 2, 3, 4, and so on and so forth. Well, if we use 1, 2, 3, 4 for P, we'll just plug them into the function. Okay, and let's see if our results come out to T. So when we do 3 times 1 minus 1, we get 2. Then we get 5 for the next one. The next one 8, the next one 11. So P does map onto set T. But how do we exactly prove it? We know that we're doing it, physics, like with the example here, that with the function, it does map to it, but how do we prove it? So we just use the same rules for same cardinality. We have to prove it's injective, sorry for my writing, and surjective. So I'm just going to write down very quickly the injective and surjective parts. If you guys would just like to see it or pause the video, you can. Okay, so since we proved that it's injective and surjective, it has the same cardinality. Thus, the set T is countable. Now we're going to prove for uncountability. So our proof for uncountability, we know that uncountability can only happen when there is no one-to-one relation. So let's say that we give a basic idea of having a set E that has a cardinality of 3 and a set F that has a cardinality of 5. Well, in this case, there wouldn't really be a one-to-one correlation because we would be left with a domain or a codomain of 3 on either side. So then let me provide an example. And in this example, we're going to use Cartan's diagonal argument. So let's say we have a list of real numbers in between the interval of 0 and 1. Remember, our list is in real numbers, so okay. So we're just going to pick out random numbers, and it goes on and on and on forever. Well, I bet I could find one number that is not in this list. So this is where the diagonal argument comes in. Let's say I take this number. So I have 0. And add 1 to it. So 0.3. I don't care about these anymore since I'm going diagonally this way. So then I take this number. I add another one. This number. Another one. This number. And there we go. So I have given you a number that does not belong in this list. And yet I could give you an infinite more numbers that are not in this list. Like, for example, if I subtract 1, if I add 2, if I subtract 2, there's going to be an infinite amount of numbers that are not within this interval of 0 and 1. So because there aren't any more amount of numbers that aren't between 0 and 1, then the interval of 0 and 1 is not countable. So thank you very much for listening to our video, and hopefully this was helpful to understand the topic of cardinality.